A solenoid has 3000 turns and a length of 80 cm and a cross-sectional area of 64 cm square. Find the self-inductance of the solenoid. Again, they don't mention that there's changing current, so you should probably expect that they'll be not asking for things related to the induced EMF. So this equation is now out of the window. It's not related at all. So you are left with either N phi over A, N phi over I for self-inductance, or you can break it open. In this case, this is solenoid. If you break it open, it will become L mu naught N square A over L. Okay, so over here, you know that they have described the geometry of the solenoid very clearly. They already tell that the length of solenoid is 80 cm, then it has 3000 turns, and it has a cross-sectional area of 64 cm squared. So all these things here are trying to describe the shape of the solenoid, describing the geometry of the solenoid. So you know that it will not be so general as magnetic flux. You need to break the magnetic flux open so that you can re-express it as in terms of the geometry of the solenoid, which is the area of the solenoid, the length of the solenoid, and the number of turns of the solenoid. Okay, so in this case, you have to break it open. You cannot keep it general. So this will be the equation you use. Okay, so L will be equals to mu naught N square A over L. So we know that the permeability of free space is 4 pi times 10 to the power negative 7. The number of turns is 3000 square. The cross-sectional area is 64 cm square. Change to meter times 10 to the power negative 4. Divide by the length of the solenoid, which is 80 cm. Change to 0.80 meter. Okay, so if you do everything correctly, put it into your calculator, you should be able to get 9.05 times 10 to the power of negative 2 Henry. So this will be the inductance, the self-inductance of the solenoid. If it has 3000 turns, if you have 80 cm length, if you have 60 cm square, it's cross-sectional area. So I hope you are able to notice that the inductance here doesn't depend on the current flowing through it. So it means that if I put 1 ampere of current flowing through the solenoid, it will still be this self-inductance. If I put 2 ampere flowing through a solenoid, the self-inductance is still 9.05 times 10 to the power of negative 2 Henry. The self-inductance doesn't depend on the current. Okay, the self-inductance again depends on the geometry of the circuit conductors, which is the number of turns, the cross-section area, the length, the radius of the circular coil, those kind of things. Those are the shape of the geometry of the circuit conductors, and it depends on the magnetic permeability, which is this mu naught over here. Nothing else. It doesn't depend on the current flowing through it. It doesn't depend on how fast you change the current. Current is not related. Okay, it's all depending on the shape of the things of the inductor that you have, and if there's any iron core or any kind of material inserted into the inductor. That's all. Okay, it's just like capacitor. You remember capacitance? Okay, capacitance, you learn that C is equal to Q over V, right? But you know that if you increase Q, it doesn't change C. If you increase V, it doesn't change C. C only depends on epsilon A over D. Okay, you can change it into epsilon. Okay, so it depends on the area, it depends on the distance between the plate, and it depends on the dielectric constant. This is not dielectric constant, this is dielectric constant multiplied by the permittivity of free space. Let me write in different form. Let me write like this. Okay, so this one is related to the permittivity. This one is related to the area. This one is related to the distance between plate. So all these here are related to the geometry of the capacitor. Geometry means by the shape of the capacitor, the area of the capacitor, the distance between the capacitor. Those are the shape, the geometry, and also depends on the permittivity, whether you insert any material in between the plate. So it's the same idea over here. The inductance here is used to represent the relationship between the change of current and the magnetic and the induced EMF. But if you increase the current, it doesn't cause a change to the inductance. The inductance won't change due to the change of current over here. The inductance won't change due to you have a different induced EMF. Okay, the L here is constant, just like the C here is constant. The C here is constant, just like the L here is constant. The L only depends on the geometry of the circuit conductor, which is the number of turns, the area, the length of the solenoid. Those are the shape and the geometry, and whether you insert any material to change the magnetic, to change the permeability. So that is the mu naught. So I hope you are able to see this one is similar to this one. It's used to represent the ratio or relationship between one thing and another. In this case, capacitance is the relationship between Q and V. The inductance is the relationship between the induced EMF and the change of current. Okay, but this C here is constant. It will not change with Q and V. This L here is constant. It does not change with induced EMF and the change of current. It doesn't change. The L here doesn't change. The C over here depends on the shape of the capacitor and the material that you insert in between the capacitor. The L here depends on the shape of the inductor and what you insert inside the inductor. So I hope you are able to see that these two equations have the similar purpose to each other. Okay, ratio of something. This one is to show you it depends on what. Okay, you can also further discuss this thing further. You can discuss this further by saying that the resistance here, it's used to describe the relationship between V and I. Okay, but if you increase the I, it will not change the R. If you increase the V, it will not change the R. The R here is constant. If you change I, what change is the V? Okay, the R here is a constant. Okay, highlight R here is constant. Let me probably just write it constant. Okay, this L here is constant. This R here is constant. Again, what does the resistance depends on? The resistance depends on rho L over A. So I hope you are able to see that the L and the A are the shape of the resistor, the length of the resistor, the cross-sectional area of the resistor. It depends on the shape of the resistor, and the rho here is the material that you use to make the resistor. The rho depends on the material that you use to make the resistor. So this thing here are also having a same purpose, is to represent a ratio of something. And I hope you are able to see that this equation here are showing you what does the value depends on. It depends on the shape of the resistor, depends on the shape of the capacitor, depends on the shape of the inductor, and the material insert in between the capacitor, the material insert inside inductor, and the material used to make the resistor. Okay, so I hope you are able to see the purpose of this equation over here. There's a parallel in between the purpose of this equation.